As data scientists, people think we're magicians. They have a problem to solve. They'll come to us and we'll just wave our magic wands and all of a sudden everything will be well. Oh, what's that? You need data to be able to do data science? Well, just wave your magic wand again and I'm sure it will appear.
How many times do we have to teach you this lesson?
Let's talk about the sheer ingenuity and resourcefulness us data scientists have. A few weeks ago, we put out a video where I used data science to find the perfect Halloween trick-or-treating route for Bart Simpson. And like with all our videos, I showed it to the team before we put it out to the public. I knew the map had been a ton of work because I had spent tens of hours and more days than I cared to count smashing my head against this problem to get something that worked. But it wasn't until I showed the video and my team asked me exactly how I made it that I realized, because their reaction was one thing: wow. So, knowing that data science can appear like magic to some, I actually wanted to do a video today to break down exactly how I made one aspect of this. Because like all of our videos, we talk about data science in the context of real world topics. And yes, I did fart around for a number of days making a map of The Simpsons, but there is a reason. Because this kind of thing is used in the real world in things like town planning all the time, and it might be some of your jobs watching. So, let's frame it with real world context. Town planning and the complete lack of usable data that often comes with it. Think of it this way. Suppose you're looking to open a new school in town. The population has grown, the class sizes are far too big. We need somewhere to put those kiddos to keep those youths off the street. But it's not just about finding a vacant building and sticking them in there. There's actually a lot more that goes into it. Local demographics are important. There's no point building over the east side of town if all the families are in the west side of town, and similarly, if there's already an existing bus stop or train station, that's much easier than having to build a whole new set of infrastructure for transport. The same logic is used, for example, for companies looking to open up a new retail store. There's a whole load of information they can use to try and work this out, but there's one important thing they need: the ability to interpret it geospatially. And that's where many of these projects fall apart. I mean, it's very easy to come up with a super complex, really exciting model that takes into account all these cool new features, but often these models fall down at the first hurdle and much easier models are actually used in the end. For one really simple reason: it's really hard to get good data on town planning. So today, we're going to look at two models of doing it. First is the ideal world scenario where you have all of this data at your hands and can just get on and use it in the perfect possible way. And then we're going to look at the reality that we actually face, which is, no, we don't have good enough data, we've got to find a way to fudge it. So the holy grail of dealing with geospatial data, which is real-world map data in lay terms, is something called a shapefile. And basically, that does what it says on the tin. It enables you to get information about the shape of the actual thing with respect to the real world. The data itself is stored in things called polygons, and they lay out the perimeter of a building in real lat-long pairings so we can work out where it is in the world. It also doesn't have to be just one building. It can also be multiple buildings, so we can have like a university campus that is made up of multiple different buildings dotted around a town. And we can also take pieces out, so we can have buildings that are donut shaped, so you can get that school quad you've always wanted. And that enables us to do some pretty cool things. For example, right here is a shapefile of Texas. Pretty recognizable, right? I also have the shapefile of Houston, and now I know that Houston is a city in Texas, but if I didn't, then I could just use these shapefiles to find out that Houston is contained in Texas mathematically. If you had just one example, you'd probably just Google it, but if you've got hundreds of these columns and you need a way to do it mathematically, then shapefiles are the way to go. Another thing we can do is calculate distance. If we had demographic information and we knew all the areas that were now swarming with children, then we could use that information to build a school equidistant from all of these areas. What you see on my screen right now, these visualizations that I'm showing you, they're actually part of EvilWorks' Puff platform. Because we have bigger ambitions than just making pithy data science YouTube videos about pop culture. No, we are looking to improve the data science experience across the board through better tooling as well. I mean, how much easier is it for me to just be able to scroll through all the states here and you just look at the shapes to know that I've labeled them right, than having to manually check every single one. Our Puff platform is under active development right now, but if you'd like to know a little bit more about it and be one of the first to get access to the closed beta, you can find out more via the details in the description. And having this functionality on my screen, if I'd had this for the roads and the buildings in Springfield, my life would have been amazing and I would have made the Simpsons video in no time at all. But I'm a data scientist like you, and the reality is not like that. So I had to do it the hard way. So if you've watched my earlier video, you'll know that I had to go on a mission just to find a map of the Simpsons. So the chances of getting a shapefile were absolutely zero. I had to be creative. Now, Parsley did a pretty good job of explaining how I actually worked around this problem, so I'm actually going to let her explain it to you. Roll the footage. I had to manually go through the entire image by hand to mark the character locations. And you might be thinking here, why didn't you just ask AI to do it? I mean, that's literally the sort of thing they're good at. And I did, and they were rubbish. So it was back to me. I spent, I don't want to know how ridiculously long, manually marking the location of every single character in GIMP image editor, and when I sat back triumphantly like, I've done this, this is beautiful, I realized my next problem. Python can't read stuff from GIMP image editor, and in order to do data science with it, I need to get it into a vector face format instead. So I took a crash course in Inkscape and did the whole thing all over again, and I'm definitely not a graphic artist now by any stretch of the imagination, but I did have something that the computer could finally understand. See, I'm resourceful. I did get my note on after all. So it's this last part where I became a baby graphics designer that's a really interesting part, because that was the unlock that took me from this really cool piece of artwork into something that we can actually use. So the first thing we need to be able to do this is we need a way to identify points of interest. Those are things that we actually care about, like maybe buildings or suburbs, but in this case, I just wanted a location that I could point to that said, yeah, that character probably hangs out around there. So these are given by nodes, dots on the map that say this right here, this is important. I labeled them all too. For example, you can see this one is Millhouse, this one is Flanders, and that's really important because otherwise the computer would be able to interpret it, but I'd have absolutely no idea what's going on. Now the nodes were enough for me to build my basic graph. I could connect all of the characters together via a straight line with the as a crow flies distance. But as we saw in the previous videos, Bart can't go through walls. He's not a ghost.
Go through doors, stupid. It's not a ghost.
So we needed to do something better. This is the point where I had to start drawing paths. Quite literally, I had to use Inkscape to draw paths over the roads that Bart could viably travel. But just like real life, this was not straightforward because the roads themselves were not straight either. Now, if I'd had enough time and wasn't fed up with the amount of hours I'd put into this project already, I probably would have carefully drawn the lines over the top. But as I mentioned before, I have ADHD and there is no way that I'm doing that, so as a nerd, I just approximated them instead. Because if we take a triangle and we add a line, it becomes a square. Add another line, you get a pentagon. You add line after line after line, you get a more and more detailed shape, but if you keep on going to infinity, what you end up with is a perfect circle. So my pragmatic approach was just to use as many line segments as I had the patience for, and that was good enough for me. But you know me by now, there's always one more problem that I need to solve, and this time, it was one of my own making. You see, I was feeling quite defeated when I was manually marking each of these locations after failing to get AI to do it for me. And so I was just like clicking on the approximate location, and that's a problem. Because these locations, they were all back from the roads, and so they were hovering in space, completely disconnected from the path. Much like if the floor was lava, our computerized Bart can't reach the nodes if there's no path connecting them. My final step was to add what I dubbed connector paths between the actual nodes that I'd lazily put on there and the paths that were the real roads that I meticulously plotted. But I had to be careful here, because I put Groundskeeper Willie and Principal Skinner both at the school. But again, I did it a bit lazily, so the actual connector paths were different lengths, implying it would be much further to go to one or the other, pretty randomly. Because I didn't want this arbitrary decision to get in the way, I put all my connector paths on a different layer so I could identify them in Python and then set all their distances to 0 so that connectors didn't actually contribute to the calculation. And speaking of Python, I think we're about time to make our way over there. I mean, we've got our nodes, our paths, and the connectors as well. I think it's time to race home and show off our hard work to our computer. Unfortunately, Inkscape wasn't the only thing that I had to take a crash course in to be able to make this video. After a bit of searching around, I managed to find out about the packages that I need to be able to take my Inkscape file and actually understand it in Python. One thing to note about SVG files is they're basically XMLs under the hood, and XMLs have been around for a long time at this point, so there's loads of packages to be able to deal with them. I personally use Elementary to get all my nodes, paths, and connectors. Now, it was one thing importing the data, but it is a completely different thing actually actually using it, and I could make a whole other video in the insane hassle I had getting this into something that I can use. But in the end, I used a NetworkX package to have a beautifully connected graph that I could use for the video. So I plotted it. Here you can see this visually. All of the nodes are on the maps, but I've replaced the dots with Simpson's character icons. I am so glad that I labelled this in step 1. And in this graph, you can see I've done a similar thing with the roads, labelled their start and end point, and the roads themselves. You can also see the naff little connectors that I made that really stick out against the elegantly drawn paths of the original artwork. And so we've done it. In a short space of time, we've gone from having no idea how to represent Springfield so that the computer can understand it, into something that we can actually do data science with. And the best part is that this is transferable. You can do this exact same process with any screenshot from Google Maps. Now, one caveat that I do have to give you is this manual tracing. It is time consuming. You can do it with the trace bitmap function within Inkscape, but it's really not that accurate, and you might have to spend more time fixing it than you would have done just tracing the paths to begin with. There are some pros to the old-fashioned way of doing it, beyond just data though. If I'd used trace bitmap, I probably would have picked up every single building and every single road in Springfield, when really, I don't care about all those buildings, just the 32 Simpsons characters that actually matter to me. By manually tracing, I was able to select the features that were most important to me. Besides, you're a data scientist. What else are you going to do while waiting for your code to run anyway? Like I mentioned earlier, here at EvilWorks, we are creating something for data scientists, something that is going to make your life a whole lot easier. Want to come on that journey with us? The best way you can get involved is by joining our Discord, the Evil Lair, where there are loads of super resourceful data scientists hanging out there to help you solve your real-world problems. In the meantime, like and subscribe, and tell me in the comments, what is the weird data science workaround that you've done that you're most proud of?